metal additive manufacturing. And our presenter for the day will be Dr. Hassan. Uh, Doctor, you can take over the slides.
Okay. Thank you very much, Tony. Do you have my voice clear?
Yes, perfect, sir.
All right. Can I begin?
Yes, you can.
Perfect. Thank you very much. Good afternoon. And I believe for some of you, good morning or even good evening, wherever you are. I hope everybody has spent the day to be at the best situation. And hopefully, we're going to have a good presentation in the next hour. As the title shows, we are going to talk about metal additive manufacturing, and hopefully that would be that has been my interest in the past 20 years, and I hope it's going to be something attracting your attentions from now on. Just a brief introduction about myself. It's now the 20th year of my engagement with additive manufacturing. So yeah, I feel a bit old at this point. I started working on additive manufacturing back in 2006. And at the time, it was not really named additive manufacturing. It was more about laser deposition systems and laser powder deposition systems and so on. That led me to doing a postgraduate and postdoc research activity at University of Waterloo later on. And then as a faculty member, I started my job to teach and also do research on additive manufacturing for about 11 years. I co-founded a company to manufacture metal 3D printing systems, the ones that we talk about today. And also, in 2022, I joined Aurora Labs, the company in Perth manufacturing laser powder bed fusion systems, and worked as their technology manager. Then I found this topic to be really worth investing more. So I co-founded eMetal 3D in 2024, about mid 2024. And since then, I've been the director of eMetal 3D. And in parallel, this is my third year of working at EIT and getting to know a lot of students and doing research along with them. That has given me a potential of knowing both sides on the academic and industry side of additive manufacturing, specifically on metal additive manufacturing, not only because of the research that I've done in the past 12, 15 years of my career at university, but also this side of my business and my career as engineering manager of two SLM manufacturing companies have led me to understand the deep challenges, not only on the manufacturing side, but also on the service side of this technology. So let me just move to our agenda. So hopefully this presentation will cover these topics. As you can see, we'll talk about some classifications, some general concepts about additive manufacturing and the benefits that we can get. And the interesting part of that would be some case studies on metal AM and the design for additive manufacturing, which is relatively a new concept. So this slide alone can actually take many sessions, I would say, if not just one, to talk about the applications at different industries. I'm just showing a very precise and limited view of what you can expect of additive manufacturing at different industries. And definitely it's not limited to that. We know that, just let me, I have some, all right. In oil and gas, a lot of companies recently, specifically, and from the past decade, probably, they have started to investigate the type of components that could be manufactured with metal AM. More importantly, on the subsea industry, we know that the weight is a key challenge in subsea and also in the aerospace. These are the industries that weight reduction is really important. On the mining, also, although the weight reduction is not really critical there, uh, acquiring and finding out the proper providers and suppliers is the key factor. On the wear resistant parts, for example, on the aerospace that has been the main leader of this technology in the past decade or more, we could see very big names nowadays that are pushing forward this technology to have not only the lightweight structure, but also new alloys and high performance alloying systems for moving and stationary parts in aerospace components. And when we get to the manufacturing in general, there are so many applications that we can't really name them, because if we name them, we will definitely miss many of them. Whatever could be manufactured out of metal can be a candidate, but by considering the limitations, which we are going to talk about in a minute. So let's have a brief introduction. What we actually talk and what we actually name as additive manufacturing. So in general, we know that we have three different methods of manufacturing: two traditional ones of material removal and forming, which basically material removal starts with the bulk and we start removing the material. The forming has a mold that, whether it is casting or forging or any process like that, the part is formed toward the press force or the high temperature and so on. And then we have the third one, additive manufacturing, which layer by layer the part is made. It is surprisingly not a new method of manufacturing. Probably we can say even the first invention of humans by making their houses years and thousands of years back by putting bricks and stones on top of one another. They were using that for manufacturing. It's not really new. What is new in there is the actual manufacturing of industrial parts with this technology, which now we can say about 4 decades is passed from the first invention of 3D printing, 3D printers. So nowadays, we're not talking about a new technology, but we have to really learn about the technology limitations and the capabilities and the new aspects of that. To clarify, I need to really take a moment on defining what we call metal 3D printing. Out of this ASTM classification of 7 different categories of additive manufacturing, as you can see in this left figure, there are 7 categories, all over 25 or to 30 different technologies are divided into 7 technologies, 7 categories. Out of these 7, 5 of them are able to manufacture parts out of metal. So when we talk about metal 3D printing, we are not just talking about 1 or 2 specific technologies. We're talking about maybe 5 different categories, which in which category you may have multiple technologies. But not all of them have the same potential. So that is my point, and I'm going to talk about it in the next slide. So this slide probably shows a clear view of what we are talking about. The left 2 technologies of PBF and DED are the actual metal AM technologies that can deliver functional, high quality metal parts in one step. So basically, you have the CAD model, you go through some process, the machine makes the part, and you have the printed part, and there is no further action needed actually to make this part ready to use. Of course, there are some post-processing activities, but they are not a part of the actual process. And we have 3 other technologies that they are indirect metal 3D printing technologies. And by that, I mean you actually have metal material in the form of powder embedded in a matrix of a polymer that acts as a binder to bind those particles together. And as you can imagine, this first step of indirect printing is not really metal. It's a composite of metal and polymer. And once we go through the next step of washing the polymer and then sintering the whole part, we end up having a part that is mostly metal, or we can even say it is all metal. But unfortunately, it is not fully dense. And we have the issue of having porosity and high shrinkage during that process. So the main distinction between these two categories is the direct metal printing technologies, which are the left two, and the indirect methods, which are the right, the three on the right. The two on the left also, they have subcategories. The PBF, which is a very well-known technology nowadays, and this is something that we are going to talk about, has two main subjects of SLM, selective laser melting, and EBM, electron beam melting. SLM is the technology invented quite many years back. It is the continuation of SLS, which is the technology using laser and polymer, but then they decided to choose to use metal powder, and that is how it started, probably more than 20 years ago. And EBM is a newer technology that uses electron beam instead of laser. So these two technologies, one uses laser, one uses electron beam, and both have a bed of powder that spreads the powder on top, and then the energy melts the powder and it sticks to the next layer. So I'm going to show a video clip that introduces more. The other three subcategories of DED are the ones that are using either laser or high speed of particles or arc to actually work and melt the material and 3D print. They are basically can be considered as a welding process. So WAM, W-A-A-M, for example, is a technology of welding, but they have added proper software that they can continuously adding the material in welding process, and layer by layer they can make the part up. So WAM, the second one, the MPA has also different names, that when you have high speed of material shooting to the surface, that very high speed provides cold welding and generates a bonding between the material already deposited and the new material that is injected, and that is how the material is made. So we have a Australian company manufacturing these type of machines, Speed 3D, and also we have lens technology that is the technology that has been I did my PhD on in 2006, which is that we have a blown powder and laser in the middle that works as a welding process, that instead of a wire, you're actually using powder to weld and basically to deposit. It's interesting to know that all three technologies of the DED category, they have manufacturers in Australia. We have a company in Sydney, Laser Bond for lens. We have Speed 3D for the second one, and we have AML 3D in Adelaide for the third one that are manufacturing this technology. There are many applications and there are so much to talk about on this slide, but I will move on to just not miss the time. Hopefully, if you have some questions, I will be happy to answer at the end. This is a movie showing the process. The sound is not really needed. I just hear the sound. So this technology starts with CAD model. We talk about CAD model means it can come from a design in computer, or it can come from a reverse engineering process, 3D scanning. Anyway, you need to have a CAD file. Once you have the CAD file, you go through the support design process, where you actually design the support structures, and the support structure will let us how overcome the difficulties during the process, as you can see. And we slice the parts based on the layer thickness that is critical for us. The layer thickness, we talk about tens of micron. So it is about 30 micron, 40 to maybe 100 micron, or even more. The layer thickness is, and these are the layers that you can actually see, and all the parameters, including the laser movements, are the tracks that you can actually see in this movement. So everything is predefined in the software and then transformed into the machine. Then the machine starts by taking the information from the software and sending through the laser system and scanning system to precisely find where the laser has to move and melt the part. And as you can see, a very thin layer of powder, you actually don't see the previous layer because the layer is about 60 micron here. But once the process is over, you'll see the next layer come over and you won't see the previous layer anymore. Wherever is melted is the part, and wherever is not melted stays as a powder, and the powder will be reused in the next process. So that is the main advantage, biggest advantage of technology, that actually the material waste is very, very low because of actually reusing the powder after printing. So as you can see, the part removal happens right after, so the speed has been increased so that it doesn't take much time. So as you can see, the person has to have proper safety gears, mask, and the anti-static hose. The powder is taken off from the part, and as you can see, what is left, it's about 40-45 hours after the process. Of course, the whole process took about 45 hours, and then the parts are pulled out. This batch is about 16 or 14 kilograms of deposition, so that is roughly what we can say. So that is the end of the process for printing, but obviously you need to do some post-processing. For example, we need to get rid of all the supports that we added. The supports are not meant to be there. We had to put it there because we have overhangs, we have some limitations. We need to make sure that the part comes out properly. And if the surface requires more quality, then we can also do post-machining and make that.
So he has to do.
Any problem, Tony? Okay. So this is a 3D scanning step that you may do or not, do not. Just the step that you sometimes take to make sure the quality of the printed part is good enough and match with the desired CAD file. So in this process, the scanned part is taken by the software and is mapped with the actual STL file. And
excuse me, doctor.
Yes.
Excuse me, doctor. Is it possible to either just lower your volume or mute the video? Because I can't hear anything, and I'm assuming the attendees also can't hear anything. Is it possible to mute the?
Is it mute now?
It's mute. Yes, that's perfect. That's perfect.
Okay. So do I have to repeat whatever I said?
Not necessarily. I think you can just carry on.
Okay. All right. Sorry about that. So I was just saying that this last step is a inspection and quality control step that you can measure and quantify the deviations from the printed part and the actual CAD file. So these are some examples of the 3D printed parts, and well, you can see some examples on the technology, the medical sections, on the variety of applications. So when you talk about material, this technology has started with probably few materials, not really very wide. But throughout the past 15 years, I would say, the number of materials to be printed has expanded a lot. So this list is relatively small yet, and I haven't put all the materials in there. But as you can see, there are a number of materials that could be chosen from this list. On the other hand, there might be some materials that you would look for and you can't actually see them. For example, where is the plain carbon steel or 4140 or something like that? The materials that are very common at industry. That's right. Not all materials are yet not all materials are printable at one point, and not all materials are worth printing. That's another point. Because of that, we need the engineers to actually think about some replacement at some points and finding better solutions, or finding solutions that actually can meet their needs. So that is sometimes needed, and maybe in the future the expansion happens. When we talk about materials, they're not necessarily conventional materials. There are new materials like the CP1, for example. There are materials that are dedicated for metal 3D printing. They have been designed for additive manufacturing. And for example, I will probably have an example when I reach there. I will show you. But they provide specific properties that you can actually expect from conventional alloys. When we talk about properties, the main question that I always receive is, what is inside? How does inside look like? Do we expect any porosity? Do we expect any lack of fusion or something? Well, the fact is we can't really say it is 100% dense, but the fact is it is dense enough to say it is fully dense. The density is over 99.5, and in many cases over 99.9%, which, if you know, casting, for example, has much higher percentage of porosity. 2-3% is very common in casting. So when you talk about 99.5 and plus percentage of density, it is considered to be fully dense. Because it is fully dense, it can be actually polished to the mirror surface, something that you can't really expect from, for example, technology, metallurgy powder technology, because that is not fully dense, so you can't actually get to a very shiny surface, but here you can. The surface area is not fully shiny, as some of the examples on the movie also showed, because we are talking about powder, and the powder is rough at the surface. So what happens is there will be some roughness at the surface. The roughness changes from 5-6 RA to sometimes larger, sometimes less. We had experiences of like 2 micron and sometimes 8 and 9, depending again on many parameters, including the powder size and also other aspects of the parameters. Exceptional mechanical properties is another function. I will show that in the next slide. And also high dimensional accuracy. We are talking about 50 micron plus minus accuracy, which is good enough for many applications. But obviously, when you're talking about fitting surfaces and also high tolerances, we need to expect some post-processing like machining or grinding to happen. But the actual free the as printed part is good enough for many applications. This table, which is quite small for myself, I hope you have it larger, shows the properties for some of the typical alloys, like stainless steel 316. This stainless steel is widely used in industry. Just to know, the yield strength of round bar of 316 in the market is about 220, 230 megapascal for the yield strength. And as you can see here, it is 500 plus yield strength. So we are expecting double the strength when you 3D print that material. So we are not actually talking about some missing properties or lowering the standards, but also we're talking about hiring and increasing the standards of the strength we expect. In other materials at the same time, for example, titanium, you expect titanium when it is very high strength to have low elongation. But as you can see here, the strength is high. It can go beyond 1,000 to 12,000 megapascal, and also having 10 plus percentage of elongation. And the same for other materials. You see some heat treated properties as well. That heat treatment is not the necessary for the process. It is not like, for example, metal FDM that requires sintering process to become metal. But this heat treatment is just the metallurgical improvement of the material that is already fully dense, but you actually expect the metallography and metallurgy of that to be stronger or better in some sense. So heat treatment sometimes becomes the extra step you need to follow if you want to get special properties. Well, so let's have a look at some key properties and why, if we really don't use technology, we are really missing an opportunity. One of the advantages of metal AM is less material waste, and I just talked about that, and you can actually imagine why. But to have some better idea, there is a parameter called buy to fly ratio, and buy to fly ratio means the ratio between the actual raw material you buy and the actual final part that you deliver, and the ratio between the two tell us how much material you're wasting. So it is very common to have in aerospace specifically that the material has to be thin enough and light enough. That ratio reaches to like 11 to 1 or even 30 to 1, means 30 times more you're wasting material than you are using it. But then when we talk about additive manufacturing, that number can go down to 2 or even less. Means if you have 1 kilogram part at the end, you're using at most like 2 kilograms of raw material. So that's a huge difference between the two technologies. The next benefit would be the carbon footprint, which is something interestingly growing in the past few years, or even decade, I would say. But recently it's been attracting a lot of attention. And when you talk about carbon footprint, definitely one part of that comes from the less waste, because we know for manufacturing every kilogram of raw material, we are generating a lot of carbon. But not only that, of course, that is a big part, but also when you talk about less weight, that means we are also using less energy to move the part. We are also using less energy to fly, for example. We have a part consolidation concept that I will talk about that at the end of this presentation. That means instead of manufacturing multiple parts and then joining together, actually you can make them in one row. And that means you are excluding a lot of extra steps of manufacturing and welding and post-processing. So that can also help to lower the carbon footprint. On-demand production also helps the society very well, because when we talk about on-demand production, that means that we produce whenever we want. We don't have to produce and put them in stock for a long time. So that is another advantage. And also we have the capability of repairing and reusing the broken parts by additive manufacturing. So because of all these, we definitely can see less carbon footprint. But at the same time, don't forget that manufacturing powder is producing a lot of carbon. So we shouldn't really forget that. But by the other advantages, that would be something to consider. Another advantage of metal AM is design freedom. So when we talk about design freedom, designers actually would be very happy about that, because, well, let's just look at this image. That's the best example, probably. No one could ever think about a manufacturing process that can finally end up with such a design. This is extremely difficult or impossible sometimes to manufacture something in one go, and that's really important. You may design multiple parts, forming and casting and rolling and all sort of things, and then weld them together, but you cannot really do it in one row. And that is really important to know when you talk about design freedom. That gives us the opportunity to rethink about all the constraints that you had in mind. And probably that is the most difficult section of probably that is the most important barrier in using this technology, because the designers have to start rethinking about all the constraints they have in mind. Rapid production. Sometimes when we say rapid, we expect 1 hour, 2 hours, or maybe if 10 hours. But we had prints that takes 3 days, for example. Can we call it rapid? There are large machines in the market that one print can take 1 month. And it is not really easy to call them rapid. But if you consider the other methods and the multiple steps that you have to go through, then definitely that is considered rapid. We have received many cases that one order came like uh, on Wednesday and delivered on Monday, because we can actually run the machine overnight, and there is no limitation on that. So because of that, that is a really game changer in the uh, supply chain for many parts, specifically in Australia, that we have really difficult time sometimes to get what we need from overseas. Superior mechanical properties. So that's what I just talked about. That we are not talking about losing um, strength. We are actually talking about improving and even using higher quality and higher strength parts. So that is really important to know. Weight reduction is coming from the fact that we are free in design. So that freedom in the design will lead to weight reduction. So one would say, why do we need to reduce the weight if we don't need that? For example, in mining, who cares if I reduce that part from 2 kilograms to 1 kilogram? Well, that's right, probably for some applications. But if we don't do that, probably we can't really get the benefit of this technology right away, because the cost of manufacturing becomes very high. This technology, the complexity is not really important in the price, but the weight is very important. So this part, as you can see, is very complex. But if you just fill all those holes and make it a simpler part, that becomes more expensive. And that is the difference between the CNC machining and additive manufacturing or metal additive manufacturing. In CNC, complexity usually means more cost. In additive manufacturing, complexity doesn't bring extra cost. But if you can reduce the weight, we should consider that to make the benefit of this technology and make the part really make it reasonable to print. And wide range of material, I've already talked about that. And this is the one I wanted to show you. For example, this alloy has been developed by Constellium, a company in French, a French company, sorry. And they have been claiming, as you can see, this is the typical aluminum Si10Mg material in the middle, and the green shows the properties of this CP1 head alloy. As you can see, in many items, in all items, I would say, you can see the advantages. So as can be seen here, the surface finish, for example, or the strength, or more importantly, the thermal conductivity, which is very important for heat exchangers, for example. The thermal conductivity is about, I think, about double or maybe a bit less, 80% more than the typical aluminum that is used in this technology. And that is really, really interesting to find these properties. So you can see a lot of information like that for other alloys that are being developed nowadays in the market. And the next one is the topology optimization. it is quite similar to the weight reduction that I just mentioned, but it's more about using the softwares to tell us what would be the best design. As you can see, probably no human can come up with such designs. They are mostly um, software driven designs, and usually they start with our typical engineer design part. Then you tell the software that I have this much load, I want I have these constraints. For example, here has to be clamped, and my objective is to reduce the weight. And the software, with the aid of processing capabilities and AI, will go through multiple steps, try and error, and finally give you some options. And you will choose, okay, I will go with this design because, well, that's definitely does the job. And also, it has less weight and much less cost for manufacturing. The similar process has gone through for these two. For those who might be interested to follow up this topic, there is the generative design topic is something to follow up. Fusion 360 has this toolbar, and Topology also has this toolbar. And if you're interested, there are very good potential in the future that if one knows how to deal with this type of features in these softwares, has a lot of potentials for future, because you will see parts in the market in the machines very soon to be in this shape. And probably the last benefit of Metal AM, I would call it as part consolidation. This is a very nice example of one part on the right side, which if you want to do it in a traditional way, you have to make all these parts on the left to finally get the same application or the same usage of the right one. So it is not really difficult to imagine how many drawings, how many inspection steps, how many welding process maybe or joining processes and tolerances and everything has to be taken into account when we are dealing with so many parts. But the other one, everything in one step happens. Definitely we need to consider many things. It is not just a simple step, but if we take over all those difficulties, then the final part is much less expensive, reliable, and easier to handle. If anything happens and we want to replace it, definitely we can think about replacement faster. All right, then we get to the next step of our presentation. We are right on time. I'm going to finish in about 10 minutes, hopefully, and then we'll have time for question and answers. All right. One of the examples of applications would be hydraulic manifolds. Hydraulic manifolds, as one of key industrial components, have been used with the traditional methods for many, many years. It is not something really surprising, but the ones who are in this industry know that how difficult that is when we are especially dealing with a block like this. You should drill many holes, vertical, horizontal, and in order to make some passages from right plane to the top plane, for example, should drill one horizontal hole, one from the top, and then block the other side. So you see many caps are put in there, and obviously all of them, they are 90-degree holes connected to one another. They are very heavy. They are pressure drop is relatively high, and they take a lot of space because of how they look like. But have a look at this project. This project was defined by Atlas Copco in 2017 at University of Lund University in Sweden. And again, it was defined in 2020 in Auckland University in New Zealand. So the first round, the project was modifying this block. What was the problem? It was 16.2 kilograms, and they wanted to reduce the weight and make the efficiency in a better way. So that was the objective, and that was started in 2017, about 9 years ago. What happened was, this is the outcome. They came up with a design that, well, that was relatively good, less weight, but the design was so that they had to put a lot of supports to make it. And that support provided a lot of challenge after printing when they wanted to remove the supports. So that is why in 2020 they defined the project again, and the engineers at the next round they came up with this design. So as you can see, the all the imports and inlet outlets, they are the same, but they came up with the different orientation for the printing and modifying all the connections between the tubes so that they don't need to have actually much supports, and instead they're using the actual um, tubes holders as the support as well, and reducing to 2% just for the support. And with that, they could actually make a huge step. So this is the design process. So everything starts with the block. So that comes with the designers of the hydraulic manifold. They tell us how many inlet, outlet, and what are the connections look like. And the next round, they start to consider a minimum thickness for everywhere. So we know that what the pressure is, we know what the diameters are. Then we assume that 2 millimeter thickness, 3 millimeter thickness from that material is enough. So everywhere should have that thickness. And then they get rid of all the sharp corners by making fillets and so on. So what is left is connection between these pipes, because you can't have some pipes hanging around with such high pressure. So they added extra latch and connections and extra walls and things, so that not only they're there, but also they are helping to not needing any supports. So the summary was this part. As you can see, 1.4 kilograms, more than 90% weight reduction, 24 hours of print, and it can handle alluvial pressure of 660, 680 bars, which is really huge. So this is a very nice example, although there are many companies nowadays. I have removed it from this presentation. It's going to be very lengthy, but there are many companies nowadays in the market that they have their products in the manufacturing line using additive manufacturing for even small hydraulic valves. The next story is about this microphone. So this is a very interesting challenge that this company, Dr. Elian Smith, brought to us. And what was the problem? The problem was this old design microphone was the main issue was it was discontinued. So the frame, which was two separate boxes, was imported from China, and that company was not manufacturing them anymore. And plus the mesh plates on both sides, plus this section which was manufactured and then assembled. Altogether, that was a challenge. The person, the manager came to us, was asking to print exactly what it looks like. So he was happy with that. Maybe not very happy, but it was working. So he asked us whether we can print it. Uh, we asked about the difficulties he had. When you talk about the manufacture, the assembly process that takes about maybe 12 parts per week, he can assemble 12 microphones per week, then realize that this is not really the right design. So let's think about a way that we actually can get rid of all those extra steps of assembling. So instead of having two pieces and then extra caps to cover and then extra connection, let's consolidate all together and make them as one part to just having some screws making together. So that is where it started. We came up with, because the Alien 8 is the name of this model, we first started with the 8 shape design, but he didn't like it. So we moved to the square design. And in multiple trial and errors, we find out that we can actually print the mesh structure directly. So this is the mesh directly printed with the part. Um, about 12, 13 rounds of print of try and error really happened. I'm just showing that in brief. And one of the last ones, probably you can see here, that there are some supports here that are not here. And that means we had another improvement to reduce the time for the post-processing time. When you're dealing with just one part, one time, you don't really think about that. But this is about 40, 40 per month. So we had to make 40 per month. And think about even more. It forced us to really think about optimizing every single step. So post-processing was a key step that was taking a lot of time. That is why we reduced the support even from this much to a very small support that you actually can see it here. And that reduced 2 hours of printing as well. So that was a saving in time, the money as well. And this is the application of this microphone now sitting on a drum. And there are a lot of users now across the world of this microphone. Another example is high efficiency heat exchangers. You have heard about that probably here and there. There are many video clips out there that you can see that. But why it is important? Why it is important to for these heat exchangers? It goes back to the capability that this technology gives us. These are the list of benefits that we can have. For example, one of the main ones is the large surface area per unit volume. If you want to have the capacity of specific capacity for heat removal from a system, you need to have, for example, 1 square meter of surface area, and that's 1 square meter means this much volume. But then you use this technology and you can reduce the volume to smaller one, because you can use the surfaces that are very complicated, but they provide the high surface area. Another benefits would be it's very compact and lightweight. Obviously, for mobile systems, automobiles and aerospace and everything, it is very, very small. You don't need to have any brazing, and by consolidation of the casing and internal parts and all the shims and everything would be in one go, and that would be much saving in time and cost. There is no leakage. Fluid flow can be optimized, so all sharp corners are gone, all potentials of pressure drop are gone, and heat exchangers can be corrosion resistant. It doesn't have to be aluminum. We have some orders from companies that they have heat exchangers in very harsh environments, so they print it out of stainless steel. And we know that it's not that easy to do it in the conventional methods. And also, so it is rapid development and iteration are possible, so you can actually optimize and customize your heat exchangers for the benefits you know. So we have companies like Hydro and PWR. PWR is an Australian company that are manufacturing their heat exchangers based on additive manufacturing. And one last example is the new generation of Apple Watch. Probably this is the importance of Apple Watch is not only because it's Apple and it could be companies using the technology, but Apple has changed some previously assumption about additive manufacturing to the next level. Whenever I used to teach to students in the past maybe 5-10 years, I always used to say when we are dealing with low numbers, additive manufacturing is good. But when we are dealing with high numbers, AM is not really the option. But this is probably the first global example that one is using this additive manufacturing technology to manufacture in the order of millions. And it was like a very secret news 2 years ago, but now we can see that product is in the market. As you can see, this is SLM technology. They have fit many of these casings in one batch, and the post-processing happens. These are the claims that the company has. 100% aerospace recycled titanium. These are just big words to attract attention, but this is titanium. But also it says 50% less raw material is used comparing to the previous ones, and that is interesting. 400 plus tons of material waste, material is saved basically, or less waste is happening. So with that, the examples are done. I just take a few moments about design for additive manufacturing. All these benefits are only be used if we take the design for additive manufacturing seriously. We can't say if this part, for example, the left one, has been manufactured by CNC, I want to do it with SLM and it should work well. Obviously, SLM can print that, but it's going to be like triple the price of the CNC or even more. If you want to really use AM in a serious way, you need to think differently. So it has to be in a different way. I don't say it is for all cases, but in some cases, it's really important to really think about our of the benefits. So here is some key factors of the design for additive. One is design for the correct AM process. So there are some general rules about additive manufacturing that many people know, the ones that they have, probably you have a plastic printer at home, but the limitations on that plastic printer are different from the metal printer or from DED printer. So we should really know what technology we are going to use. So all the minimum feature size, accuracy, and so on, they are definitely depending on what type of technology you're using. Design for minimal usage. Don't think that if the client doesn't need to reduce weight, so why I bother myself? It is important to consider the opportunities and options like mesh structures and so on to reduce the weight. That is how we can have the additive manufacturing really showing its potential. Thinking of improving functionality, there are so many applications on using internal channels, for example, internal cooling channels for many applications that have never been even thought of because they were not possible. But now you can think of having internal cooling channels, for example, in your plastic mold, and that can change everything. And also design for part consolidation. If we think about that, definitely we can get a lot of advantages out of this technology. So that would be my last slide. Just quickly saying that we are planning with EIT to have a workshop on additive manufacturing. The workshop would be a 3-day workshop with extensive topics, whatever I just mentioned. We will go through more details, and also we will have a live show of the process. That is how we can get more sense about what is really happening. Live post-processing, live printing, and some software applications that hopefully EIT will announce that soon. So thank you very much. I'll be happy to take some questions.
Thank you very much, Doctor. Thank you very much. I think that was a very excellent and informative session. And I just saw one of the attendees just said the same also. So thank you very much, Doctor. So we are at the end of the session. So these are some of the courses that today's topic covers. So these are some professional certificate. You have advanced diplomas, graduate certificate. You can just check on our. You can check our website for more information and for more courses. You can also inquire. You will then get a feedback or a call from a course advisor that will be able to assist you throughout your inquiry. And we're moving on. So this will be the upcoming courses. We have a range of courses in mechanical engineering. As you can see on the right hand side, those are the start date respectively for different programs. So you are welcome to apply for any if you are interested. As I've said, below these are the link for our website. So if you want to inquire of any other information and other courses, you can, and you will be assisted. So on your screen now, this is the certificate of attendance QR code, so you can scan to claim your certificate of attendance. And also, I will be sharing a link just now on the chat box to get your certificate of attendance.
Very good.
So yeah, yes. So this is the Q&A. So I'm not sure if Doctor you can see the questions, or I'll just read out
I
the
have seen
questions for you.
some questions there, some very high level, and some questions in the chat section. I'll take a few. How much time do we have? It's already 3 o'clock, but is it okay if it takes like five
Yes,
minutes
fine.
or
It's
is that okay?
okay. It's okay. It's
Right.
okay. Yes.
Very good. Thank you very much, everyone, for listening. And I'll try to take some of these questions. Sorry if I missed some. I have my email address there, so you can email me if you want to really get into more details. One of the questions would be about the thermal history. So that is a very good question. Definitely, we are talking about a very fine welding process. So the temperature at the melt pool is over 2000 degrees C, and that means we are dealing with a lot of stress and thermal stress and residual stress happening. What happens is we have some challenges with the thermal stresses. We need to consider that in that workshop. Hopefully, I will show you some examples of how we deal with that. There are some general rules how to control the distortions happening, but at the same time, there are some softwares that actually we can use and predict what's going to happen, and then based on that we modify the file so that we can control that distortion. One question is about, is the metal coming out is very hot? Well, definitely we have to wait. We usually wait about 2 hours, 1 to 2 hours to cool down. It is quite hot. Definitely it has a preheating of 100 degrees C, but it is usually more than that when the process is over right after, but it cools down slowly because it's in a pack of powder, and powder is not really a good um, thermal conductivity. They have a question: how does metal additive manufacturing address the challenges of production large-scale components using renewable energy systems? Well, large scale, I probably consider that in size wise or number wise. We have in the size wise, we have 2 meter by 2 meter maximum printing volume that we have 2 meter by 2 meter for about 1 or 1.5 meter, which is the E plus 3D part machine. And that machine has 64 lasers. So that has been the largest laser powder bed fusion system ever made. But usually it is not made for very large parts. They're usually made for many parts to be printed at the same time. The reason for that is we are dealing with a very complicated, stress intensive process that controlling that is quite complicated. Uh, Still, we cannot really 3D print with this technology. There are other technologies, like DED technology, for example, has less limitations on size, or maybe no limitations. So as far as you can reach the arm of the robot, you can actually reach, but the quality and the resolution is definitely different. So I would say on the size, there are opportunities now. I remember I used to say 40 by 40 is the maximum size of printers, but now 2 meter by 2 meter is even exist, and that is very interesting to know. The question is, when the metals are printed, are they reinforced by high pressure? Not at all. In this technology, we're talking about LPBF, laser powder bed fusion. In this technology, there is no reinforcement or pressure. It's a free-form method that actually it is melted. So the powder is melted to the previous layer, and that melting helps to stick to keep everything together. So it's like a welding process that happens thousands of times to make a part. Um, so I'm just scrolling the questions. Well, about handling powder and reusing that, there are some guidelines we should follow. Definitely, powder handling is critical not only for the health of the person using that, but also for the reliability of the whole process. We are dealing with a process which is not traceable. We cannot really know or understand if the powder is contaminated. If the powder, if you just with your bare hand, if you touch the powder, most probably you have contaminated powder. The reason for that is a little bit of moisture or oil from your finger can get into the powder, and that can cause cracks during the process. That is why it is very, very critical to be very careful on handling the powder. So that we have color coding, we have proper gloves and masks and anti-static clothes. We have regulations on how to clean bottles, for example, vacuum cleaning and with alcohol. We consume a lot of alcohol actually for just cleaning. Everything is in a very high level cleaning stage because we cannot really take any risk. If something happens, we actually don't know because you cannot know unless something breaks. And if something breaks, you don't know if what was the reason. And that was one of the issues the time I joined the company in Australia. They had some issues regarding the cracking, and it was a big pain because they had done a lot of good work, but at the end, the part came out of the machine with some cracks and it was a failure. But after a lot of practice, we realized that there was a small contamination added to the powder, and that was the whole reason. They removed that, and everything was fine. So it's very, very critical and important, really, to understand the powder situation. Powder handling at the same time is very critical when we are dealing with large machines. For example, when we talk about 2 meter by 2 meter machine, we are dealing with a couple of $1 million uh, value of the powder, and we cannot really handle that per se by hands. Definitely, it needs a lot of machines. One of the issues about depowdering, just to know, when we make the machine, depowdering means you flip it over, shake it to have the powder coming out. When it is a small platform, you can actually handle that. It's about 10, maybe 20 to 25 kilograms. It's still a lot, but it is manageable. But when you're talking about over 100 to 200 kilograms, you cannot really do that. So there are some extra machines to be used for depowdering, and those machines also should have their own standards. One of the main challenges, I think I saw a question about that, is when you want to switch from one material to the other one. That is also a source of contamination, so you should be very careful and some regulations to follow. So uh, I would just type my email address again here because someone is asking, but you will receive um, the presentation slides shortly in the next 2 days, as Tony mentioned. So my email is just what I typed here. So I would think I would cover most of the questions. If there is any other question, I would be happy to take.
Okay, thank you, Dr. Hassan. So yeah, I think you've covered pretty much all the questions, and thank you for taking extra minutes to answer the questions. And I would like to thank all the attendees for taking their time also joining the session. I hope it was informative as it was to me. Doctor was very good throughout the presentation. We are at the end of the session. I've shared the link to the certificate of attendance. And on your screen now, these are the QR code also. You can scan this to get your certificate of attendance. Yes. In 2 business days, you will get the video, the session video. So just check your junk folder, spam folder if it does not appear in your inbox. Yes, and for any technical questions with today's topic, if you do have any, Doctor has shared his email address with you, so you are able to reach out to him if there are anything. And anything else from you, Doctor? Any last words from
Well,
you?
thank you very much. And thank you for all the attendees. Hopefully, they will follow up the topic and we'll be in touch soon. EIT is now really moving toward adding new technologies to the list of the workshops and other certificate programs. So that's a very good news. I think if they follow up the EIT events, they can follow up and get more information later.
That is great. Thank you, Dr. Hassan, once more, and thanks everyone. I think we are at the end of the session now. And I would like to yes, everyone have a great day, and you too, Doctor. Thank you very much.
Thank you. Bye-bye.
Thank you. Bye-bye.